All right, so we're going to take a look at 2.1, the atomic theory of matter. Basically, we're going to start to build the atom from kind of the ground up. Okay, so that's the premise here. So back in the day, this is 250 years ago, about Dalton developed this idea, the five postulates of matter, or five postulates of what became he was kind of the grandfather of chemistry. So first thing he said was, matter is composed of exceedingly small particles called atoms. Atoms are the smallest unit of an element. So is this true? Is this still true? Matter is composed of these small particles called atoms back in the day, back 250 years ago. It's amazing that they kind of came up, that he developed this concept. It is the smallest unit of chemistry for the most part, but it's not entirely true because we do know about subatomic particles, which we're going to see a little bit later. So for all practical purposes, yes, the atom is the smallest, but we know that there's subatomic particles and subatomic particles beyond that. So we're going to take a look at that. So postulate one, matter is composed of building units called atoms. Picture these as like the individual units, unlike versus derived units, right? All right, an element consists of only one type of atom, which basically they have the same characteristics. So elements consist of only one type of atom. Yeah, so an element's an element. Copper is copper, gold is gold, and they're going to have similar, and that's kind of the really important part here, which have identical chemical properties. We find out that isotopes kind of screw that up a little bit because, water versus heavy water, which has the higher isotopes of hydrogen, are going to make those things behave a little bit differently. Certain isotopes of uranium are going to have different properties, and they're the only things we can use for fission. And so, but again, way back 250 years ago, this is impressive. So elements contain one type of matter, and they have identical properties. They're going to behave the exact same. So they're going to behave the exact same, and we're going to talk about why the electrons make them behave the exact same. So one more time, smallest particle is an atom, and we use that to build everything. Elements consist of only one type of atom, and they have similar chemical properties. All right, next. Atoms of one element differ in properties from atoms from all other. And that's true. So elements are different, right? So I cannot simply replace carbon with silicon and have the same exact compound. So atoms of one element differ in properties from atoms of another. Basically, it's just differentiating that atoms are unique in or elements are unique in their makeup. All right, next up, a compound consists of atoms of two or more elements combined in the smallest whole number ratio. All of this states is essentially we're going to build atoms, we're going to build compounds out of the atoms that we have, and we're going to end up with whole number atoms, right? So this is copper 2 oxide, or CuO, right? So we have copper 2 oxide here, CuO, and it's a 1-to-1 ratio. I'm not going to have Cu 0.5 and O 2.3 or some version of that. They're always going to divide to the smallest whole number ratio, which is true for pretty much everything that we're doing. But nowadays, these modern materials, we kind of, not really necessarily compounds, but we kind of take advantage of that. We start doping things. So I might replace an arsenic with phosphorus. And so my equations get really kind of strange. So it might be something like arsenic X minus 0.3, oxygen 2X, and nitrogen 0.3% or 0.3Y. So there's just some really strange terms out there. They are the smallest whole number ratio. When you break it down, basically a compound consistently consists of the same ratio of elements. Okay. And we're going to talk about that in terms of relevant laws of matter. And then finally, he said atoms are neither created nor destroyed by chemical change. And that's the important word here, chemical change. Atoms are neither created nor destroyed by chemical change, but they are instead rearranged to yield different substances, which is great. That's exactly true, right? We rearrange these things to form different substances. We do know that atoms can be created or destroyed. We have fusion, we have fission. So when we get into nuclear chemistry, that's different, but that's not really a chemical change. It's not something that we do on the bench. Okay, So relevant laws of matter, which kind of came from Dalton's laws. So law of conservation of matter, matter cannot be created nor destroyed. This example here, where I have the 2 green, the 2 blue yields this product. This is currently not balanced, okay? So we actually have to add a 2 in front of this in order to make sure it's balanced. We always need the same going in as we do coming out. So I start with 2 green, I better end with 2 green. And in fact, I do. So 2 and 2, okay? So yeah, so law of conservation of matter. Matter is neither created nor destroyed. Perfect. If we were in a situation where it was, life gets much more complicated. So it's good to know that whatever we start with, we always end with. The law of definite proportions. And again, the law of definite proportions, we've already talked about this. Law of definite proportions basically says water is water is water, or in this case, the 2 green, 1 blue, smallest whole number ratio. So this goes right back to Dalton's laws, or Dalton's postulates, okay? So it does really kind of fill in that void. That's where these things came from. And then this final one, law of multiple proportions. So law of constant composition or definite proportions basically says a compound that behaves the same is going to have the same exact setup every single time. So water will always be 2 hydrogens, 1 oxygen, it'll always behave the same. Law of multiple proportions basically says there are a number of different compounds that we can have. So what we'll notice here is I have 2 different versions of copper oxide, or copper chloride rather, right? They have different properties and they actually have different chemical makeups. So this one on the left, A, is actually copper oxide with 1, it's a 1-to-1 ratio. And the one over here is copper, it's not oxide, I'm sorry, copper chloride. It's still a 1-to-1 ratio, though. And then the one on the right-hand side is Cu, keep doing that, Cl2. It's a 1-to-2 ratio. Okay, so in that case, 1 copper for every 2 chlorides. So again, law of multiple proportions, 2 elements react to form the same one. So if I were to react 1 copper with one equivalent amount of chlorine, we usually end up with a 1-to-1. If I have an abundance of chlorine, we would end up with a 2-to-1 ratio or 1-to-2 ratio for copper to chlorine. So again, all of these basic relevant laws of matter apply to Dalton's postulates, those 5 postulates. Again, he came up with it 250 years ago. Pretty impressive that he could do that. All right, good. Discovery of the atomic structure. So this is what we know it looks like right now. The atom is composed of a nucleus and electrons around the outside. We know electron has a negative 1 charge. We know protons, neutrons have a 0 charge. Electrons have a positive 1 charge. And I have that right? Yeah, I have that right. And that's pretty much as small as we're going to go in this class. But if we actually look at a proton is made up of 2 up quarks and a down quark, because an up quark has a charge of, let's see, plus 2/3, and a down quark has negative 2/3 or negative 1/3. And then the down quark, yeah. So an up quark has a charge of plus 2/3. A down quark has a charge of negative 1/3. So you combine those together, 2 up quarks and a down quark together gives you the +1. And a neutron, if you do that math, you're going to find the 2 down quarks cancels out the 1 up quark. So again, subatomic particles are a thing, but we're going to pretty much draw the line right there. Okay, and typically we're not even going to worry about the nucleus after we discuss after we just discuss this and nuclear chemistry. So it's amazing. We can't see these things. You can only see these things with energy or really, really impressive techniques. So let's start with the cathode ray tube and J.J. Thomson's experiment. So in 1897, J.J. Thomson set up this experiment and he discovered the electron. So the discovery of the electron, essentially, we knew about cathode ray tubes. A cathode ray tube is essentially you're generating, just zoom in here, you're generating electrons, okay? Right, I'm just gonna use, we're gonna generate electrons right here. And because this anode is positively charged, you can essentially fire the electrons through because they're gonna pick up speed because they're gonna be attracted to this positive right? And you're going to get a beam of electrons. So you have this beam of electrons and you have this fluorescent screen. If you ever see one of those old CRT monitors, this is where you would actually see that. So this is, you're going to see a little dot, kind of a little blip show up right there. So in that, we have these electrically charged plates and a magnetic field, but ultimately we have these electrically charged plates. What you'll notice is these two plates, I have a negative charge on one side and a positive on the other. And of course, because this is an electromagnet, I don't need to turn it on. So if it's not on and I send the beam through, we would expect it to hit right in the center of our little fluorescent pad. Now, when he turned on that electromagnet, this beam actually diverted itself and it ended up shooting down here. So you actually saw a little dot down here. Okay, what does that tell him about an electron? Well, what that tells him about the electron is it is going to be negatively charged. Okay, so it tells him it's negatively charged because it is repelled from the positive. I'm sorry, it's repelled from the like terminal, which is negative. Okay, and it is going to be a different color here. Is going to be pushed away from the negative terminal and it's going to be pulled toward the positive terminal. It's going so fast that it doesn't absorb there or anything, but it shoots through. And that's why the fact that it's bent downward, so this thing would see that it's actually bent downward, indicates that it is in fact negatively charged. Okay, by the way, last thing, all of this stuff here in the very beginning is to just collimate to get these things to go directly towards the screen. All right, good. Next up, the Robert Millikan. So Robert Millikan came up with this other experiment where he was dropping oil drops. So the oil drops, so the oil drops were sprayed in, and then some of them made it through this little pinhole and worked their way downward. And you can fool around with this electric field, and you could increase or decrease the strength of the electric field. And what you could do is you could get one of these to just kind of settle in the middle and stop moving. Okay, so that's where the oil drop experiment got kind of interesting. So I'm just going to pause for 1 second. So if you can get one to suspend right in the middle, okay. So by the way, these things are charged. We use the little X-ray. We use the little X-ray terminal to eject, to hit the oil droplets and to knock off, to add an electron. So these things are in fact charged. And so if you imagine if they're charged, okay, if they're negatively charged, we've added an electron to these things. As they're getting closer and closer to the negative terminal, they're actually going to want to stay away from it. So they're going to travel up. So we've got two opposing forces happening here. All right, so we have, for the dropping portion of this, it's going to be mass times g, which is the force of gravity. So the mass, the weight of this thing, the mass is pushing down, and the force of gravity, which is a constant, is trying to force it downward. But we can try to force it upward with the electric field. And so the electric field is going to be, E is the strength of the electric field, and Q is the charge of the actual the charge that we're applying. So we can measure the mass of the oil droplets. We can look at the weight of the gravity on here. So ultimately what you end up with is, so let's see, I'm just going to cross out the constants. So imagine if you're letting this drop and then you get it suspended right in the middle, so it stays put. At that point, the force of the mass pulling it down is equal to the force of the electric field pulling it upward. And what do we know at this point? I know the mass, I know the force of gravity, I know the level of the electric field because I've been adjusting it to get it to stay in the middle. That leaves us with charge. Okay, so if I know the charge of this thing, that is going to tell me overall, that's going to tell me the charge. So what the Millikan's oil drop experiment told us is, well, I know the mass and I know the force of gravity. Opposing that are the electrical field and the charge that is there associated with it. So with those together, we know the charge and the mass. of an electron, because there's a little adjustment because you do gain a little bit of mass from that. But yeah, we know the charge and the mass from the electron. So at this point, we say, all right, we know what an electron looks like. And someone stipulated that, all right, we have actually, it's the plum pudding model versus the planet model, or whatever they call this. So there's two possible models for what this thing actually looks like. The plum pudding is the positive is interspersed with the electrons all there together. So they're all just kind of in this large massive stuff. Someone else said, okay, well, actually, it's a dense, there's a positive charge in the middle, and then the electrons are around the outside. So ultimately, it came down to Rutherford to come up with the proper postulate. And I like drawing this out because it kind of makes sense. So let's go through his experiment quickly. So right here, I have a lead block. And in front of this lead block, I'm going to put another lead plate with a hole in it. Okay, so both of those things are pieces of lead. And then I'm going to take some radioactive material and I'm going to put it inside this little lead block. There, see, it's a little orange, it's radioactive. And this thing is going to emit alpha particles. Okay, so an alpha particle is, it's a helium nucleus. Okay, so it's He4 2 plus, but it's positively charged. That's all that matters. Doesn't really matter other than that. So this thing would block. This thing is just going to emit radiation at random. And that's kind of how an alpha particle or a positive decay is going to work. So the problem that you run into is we need a beam of this stuff. And this is where we're going to collimate. That's the word that I'm going to use. Occasionally, you're going to get one of these alpha particles to travel. In fact, there's a decent amount of this. So you're going to get an alpha particle to travel through that hole. So anything that travels through that hole is essentially going to create the beam. Everything else gets stopped. So that's how we create a beam of positive particles. We just block every other location with lead. So here we have some positive particles going towards our target. Our target is going to be a piece of gold foil. Okay, actually, I'm going to use this, a piece of gold foil. And behind the piece of gold foil, we're going to have a photographic plate. So this photographic plate is going to pick up where anything hits. The unique part of gold is the fact that we can actually, it's so malleable and so pliable, that ductile, that we can actually create a sheet so thin that it's about 1 atom thick, 1 or 2 atoms thick. So you can create this really thin gold foil and put it in the way. So that means that we don't have to worry about going through so much matter that we're not going to understand our results. We're going to be going through like 1 or 2 rows of gold ions, or gold atoms, I should say, and see what comes out on the other end. So this told us a lot. In fact, this kind of really firmed up what the atom looked like in terms of like the simplistic model of what we actually see. So what were the results of the gold foil experiment? So the results of the gold foil experiment. So first of all, if we saw that every single thing of these went through and hit on the other side, so every single positive particle just kept hitting on the basically directly through, that would indicate that it is like a plum pudding model. There's nothing really going to block it. All the particles are either going to get absorbed by the negative charge, or they're going to go right through and they're not going to interact with anything. Again, the plum pudding model saying that most of that space is just kind of positively charged. Okay, so either they get annihilated or they just go right through. What the actual results that he saw, well, actually most of them did end up going through, but he did see some that were deflected at decent angles, and he actually saw some others that were kind of deflected completely and hit in front of the gold foil. So let's focus on this little bit here. So the ones that went right through indicate, is kind of the most important one in setting a precedent here, indicates that 1, an atom is mostly empty space. Well, it is, of course, coupled together with everything else. And so after doing more research, this is what we found. If this atom right here that I've highlighted, if this thing is the size of a golf ball, that's the size of your nucleus, okay? You would have to travel, if this is the size of a golf ball, I would have to travel 4 miles before I found another golf ball size nucleus. that is how far apart. That's how much, when I say empty space, think about that. If we blew up the nucleus to the size of a golf ball, you'd have to travel 4 miles before you found another nucleus. That's mostly empty space. We mean it. That's mostly empty space, which is crazy considering, look around you. This is, there doesn't look like mostly empty space. That's how different the world of atoms actually is. So I think it was 1 in 6,000. Let me look this up actually before I continue. So I'm going to pause quickly. Yeah. Okay. So the ones that were deflected, 1 in 8,000 of those were deflected. And what we see is if it gets close enough to a nucleus, it kind of deflects it. What does this tell us? Well, it does tell us that the positive charge exists in the nucleus, or in a very confined, in the nucleus, or a confined space. And then the thing that finally solidified this, saying it's really, really well understood, is this one right here, which deflected almost completely back. Okay, so if it hits a nucleus directly, and this happened in 1 in 20,000 of the little alpha particles would hit there. And he said that it was like firing a 15-inch shell at a piece of tissue paper and having it bounce directly back at you. Like it's that kind of crazy in terms of, in fact, when we talk about quantum mechanics a little bit later, the person who kind of came up with it said, "I'm sorry that I had ever had anything to do with this." So yeah, quantum mechanics and all of these things, it feels like magic until you understand it better. All right, finally, let's take a look at the Chadwick experiment. I'm not going to get too much in detail about this, but the last thing that we have to discover, because we now know about the proton, or the nucleus and the protons, we know about electrons. Chadwick discovered in 1932. And if you notice that Rutherford 1910, and it took us another 20 years to understand the neutron, because there was some mass, but we didn't understand exactly where it came from because we could measure protons. 1932, because it's an uncharged particle. It's really hard to measure an uncharged particle. You need a unique way to do it. And so the way that this happened is you have an alpha emitter, and you can look into the details on this. We don't really need to get into it too much. I just wanted to give credence to this. The alpha particle is going to hit the beryllium to go through a chemical reaction to produce carbon, to change it's going to go through a radioactive decay, or actually a radioactive capture of the alpha particle, and convert beryllium into carbon and a neutron. And so these are the neutrons that get launched at paraffin. Paraffin is just a bunch of carbon and hydrogen. Most importantly, once a neutron hits the paraffin, it ejects another proton, and that proton gets detected. So the gap here is kind of what they were measuring by counting the change in mass and the amount of stuff that they were seeing. So yeah, that's Chadwick's experiment to discover the neutron. So it's pretty impressive stuff considering. But yeah, all right, that's good. That's the first part, just 1 and 2.